Hi, my name is Naums, and I'll talk about how functional representation can be used to parallelize programs automatically using constraints. In general, it is difficult to optimize programs for parallel architectures because of all the low-level details they expose: shared memory, threads, vectorization. There are different ways of mapping data on heterogeneous memory and different ways to map computation on a hierarchical execution model. Here is an example of a typical GPU architecture that is often used to parallelize programs. From now on, I'll use OpenCL terminology. A GPU typically has multiple cores, which can execute multiple threads in workgroups, so one workgroup per core. There is a big chunk of global memory, DRAM, that is accessible from all the cores by all workgroups. Each core has its own local memory, SRAM or DRAM, that is shared only by the threads of a single workgroup executed on that core. Each thread has private memory registers that are not accessible by other threads. And in OpenCL program, we can index workgroups and threads in 3 dimensions. As you can see, there are a lot of low-level details that need to be considered when parallelizing a program, which calls for automatic code generators and optimizers. Parallelizing even simple programs can be non-trivial. In this example, we read a 3D array from global memory, apply function f on it, write the result into local memory, then apply function g on that result, and write the output into global memory. Notice that these two loop nests are transposed in relation to each other. So how can we parallelize this program? A naive strategy would be to parallelize this outer loop and do the rest of the work sequentially. However, this would result in undersaturated cores because each thread will end up doing a lot of sequential work here and here. We could parallelize further, but this would introduce a data race between these two accesses, so this is no good either. For synchronization, we need to use workgroups, like we do here on line 2 and 6. But this presents a different problem. Local memory is not shared between different workgroups, so the data written here is not necessarily the same data that's being read here, which results in an out-of-bounds access. This strategy is actually valid. Everything starting from line 2 is executed within the same workgroup, which lets us prevent a data race using this barrier. But barriers come with synchronization overheads, so this is not necessarily an efficient parallel strategy. This is valid and potentially efficient. Threads only read their own data, so there is no need for expensive synchronization. The current approaches are either costly to extend for new applications and new hardware because they rely on the user too much, or they use a representation such as polyhedral, which makes it hard to reason about parallelism and ends up relying too much on heuristics. The alternative approach that we are suggesting is to express the problem in a functional IR and then generalize the parallelization constraints specific to the given problem. These can be used to prevent evaluating invalid parallel strategies and optimize the search. We evaluate this technique using Lift, a functional data parallel language. Let me show you an example in Lift. Here we start with a 3D input, and we pass it to a map primitive, which is a functional pattern that can be compiled into a loop. Whether it is sequential or parallel, we get to decide that later. For now, map is just abstract. This example then iterates over the next 2 dimensions of X in map C and map D and saves each element into the private memory. It then applies some function f and stores the result in local memory. Finally, it applies function g and writes the result into global memory. This example could be an output of a previous optimization stage where we decided on this particular memory mapping. So now we have a question of how to parallelize this efficiently. Every map presents a design choice, whether it should iterate sequentially or in parallel. So we start by associating a parameter with each map. So in this example, we create 4 parameters. Then we encode the design choices as integers, and now we can generate integer constraints on these parameters, which define what a valid parallel mapping is. We chose the encoding to represent the available design choices, so that if you divide the value by 10, you get the level of parallelism, sequential, local, workgroup, or global. And if you apply a modulo 10, then you get the parallel dimension, 0, 1, or 2. And here is an example of a simple parallelization restriction. Registers cannot be accessed in parallel because they are limited in scope to a single thread. So in a functional IR, what that means is that a map that reads or writes private memory must not be parallel. In our example, map D produces a private result, so we can generate a constraint on map D. And here is the production rule that can generate this constraint. The condition is that for each map that uses private memory, the following must be true. The value of the parameter corresponding to that map must be less than 10. According to our encoding, that means that that map has to be either sequential or fused. And so we generate this constraint for map D. To respect the shared memory scope, we can also ensure that local memory is never used outside of a workgroup. Since map C writes to a local memory, we generate such constraint for map C. We generate the same constraint for map B because it reads local memory. We also generate a set of constraints to conform to the parallelization hierarchy. For example, to prevent duplicate scheduling, we ensure that 2 nested maps are never parallelized in the same way. This little example requires at least 16 constraints in total. Some of those ensuring memory scoping, that there is no ambiguous scheduling, that the hierarchy of parallelism is respected. All of these constraints make sure that we conform to the OpenCL programming model. Now that we have all constraints, we can choose a combination of map parameter values which satisfies all the constraints at the same time. We can now decode the chosen combination and parallelize the expression accordingly. Finding those combinations is a job for a constraint solver. We can use one to generate many candidates that are all valid parallelizations and evaluate them to find an optimal one. The approach also supports heuristics. The search space can be further reduced by expressing heuristics as constraints. One heuristic that we use is that we always fuse sequential maps. We evaluate this technique using convolution, which is a core operation for convolutional neural networks. We start with high-level lift expression for convolution, and then we apply a list of optimizations through automatic rewriting. These include tiling multiple times for data locality, prefetching for data reuse, mapping memory in a specific way, coalescing memory accesses, and as a result we get this. A huge intermediate expression. If we zoom in a little bit, we see that all maps are still abstract, so we need to decide how to parallelize them. And so we apply this technique. We create a parameter for each map and we let the constraint solver suggest parallel mappings that are valid. And for each candidate, we can now create an expression like this, which can now be compiled and evaluated. This plot shows achieved performance as a function of exploration duration. The performance is shown in gigaflops per second, so the higher is better. Duration is shown on a logarithmic scale. As can be seen here, manually parallelized candidate takes about 10 seconds to compile and evaluate. And this is how exploration goes with a constraint solver. It takes 95 minutes and 450 candidates to reach a peak performance. With a randomized brute force approach, it takes weeks to reach peak performance, and by the time even one valid parallel mapping is discovered, the constraint solver has already reached peak performance. We compared the peak performance of this technique using VGG16 neural network as an example on a Mali GPU. We compare against ARM compute library, which contains handcrafted, well-optimized convolutional kernels, and the TVM code generator, which produces very good kernels on a range of hardware. In terms of the time spent on all the convolution of VGG16, Lift is much better than ARM Compute direct implementation and on par with the GEM implementation. Lift also achieves a slightly better performance than TVM. Here we evaluate memory consumption, which is an important consideration for mobile devices. The consumption is shown in megabytes, so the lower the better. We can see that Lift is close to the theoretical minimum consumption of the direct method and uses 3.6 times less memory than the GEM method. It also uses 2.7 times less memory on average than TVM. To conclude the talk, an expressive IR can simplify static analysis significantly to the extent that for a given problem and a given set of hardware-specific optimizations, we can generate custom-tailored parallelization constraints. These can be used to prune the invalid candidates from the design space and thus save a lot of time during the search. And I'll end here. Thank you for checking out our talk.